Hello everyone, welcome to Clean Coder YouTube channel. So today we are going to solve this lead code problem number 162, find peak element. Again, this is a medium level lead code problem. So let's go through the problem statement. A peak element is an element that is strictly greater than its neighbors. Given an integer array nums, find a peak element and return its index. If the array contain multiple peaks, return the index to any of the peaks. You may imagine that num of -1 is equals to num of n is equals to negative infinity. You must write an algorithm that runs in O of log n time. So when he writes O of log n, immediately a light bulb in your mind should start lighting. When in which algorithm generally the time complexity is O of log of n. So the answer is pretty straightforward. It's binary search only. So let's see how we can apply binary search in this algorithm. So let's see the first example 1, 2, 3, 1. And what is the peak element here? 3. What is the index of 3? It's 0, 1, 2. 2 is the index of 3. So output is 2. Let's go to the second statement now. 1, 2, 1, 3, 5, 6, 4. Okay, this second test case we'll cover on the whiteboard, don't worry. Let's go through the constraints first. Nums length is between 1 to 1000. Okay, so each element of the array is between negative 2 raised to the power 31 to 2 raised to the power 31 minus 1. And nums of I is not equal to nums of I plus 1 for all valid I. Okay, cool. So these are the constraints. Let's go through the whiteboard now. First test case, for your convenience, I have drawn on the whiteboard on the graph. So clearly there is only one peak here, this one, and its index is 2. 3 is its value and its index is 2. So in the first test case you need to return 2. 2 is the right answer. Let's see the second example now. So this is the second example, and for convenience I have drawn the graph. So what you can see here is that there are two peaks actually. This is also a peak, this is also a peak, right? So he has clearly mentioned in the problem that you can return either of these two peaks. Both are fine, both are valid answers. So you can return either one of them. So one is also an answer, and 5 is also an answer. So you can return any one of them. Both are peaks. So now you can brainstorm a bit how you can apply binary search on this problem. So binary search, we all know, is based on divide and conquer strategy. So what it does is it divides the search space into two halves, right? And it tries to converge on one of the search space. So you need to find out now how you can apply the binary search here. Let's move to the problem statement again. Clearly you can see that in this statement he has mentioned nums of -1 is nums of n is negative infinity. By this he means that the left extreme and right extreme both have negative infinity value. Okay, so if I explain it graphically, it means something like this. So the graph would be something like this. Okay, this is also negative infinity, this is also negative infinity. Okay, and there are some peaks in between. So how you can apply binary search in this algorithm? This is just an application of modified binary search tree. Okay, so I'll tell you the simple intuition using which you can apply the binary search here. Okay, so assume there is a mountain. Okay, assume there is a mountain. This mountain, right? What could happen? You could be either on the left side of the mountain, or you could be either in the right side of the mountain. Correct. So if you are on the left side of the mountain, let's say, okay, left side of the mountain, what would happen? If I take 3 pointers on this slope, clearly, uh, first one is less than second one is less than third one, right? If I am on the this side of the slope. Similarly, if I am descending, if something like this is happening, what would happen? If I'll draw these 3 pointers again, what would be the relation between them? It would be 1 is greater than 2 is greater than 3. Correct? In the previous slide, it was 1 is less than 2 is less than 3. Now this is second scenario. Now there is also another scenario, which is this one. Okay, this is my pointer number 1, this is my pointer number 2, this is my pointer number 3. What would happen in this case? 1 is less than 2 is greater than 3. Okay, this is the condition. Clearly, if this condition comes, 2 is pointing to the top of the mountain peak, and you can break and come out of the whatever loop or recursion you are applying. So this is the breaking condition of that. Now, obviously, you need to cover two more conditions, which are actually the end conditions. Like if you are at the starting, and if you are at the starting, you need to take a bit extra care. Similarly, if you are if you are at the end, okay, you need to take a bit extra care. So this is just the intuition, and using this intuition, you can pause this video here and you can try to derive the algorithm on your own, and I'll pause for a couple of seconds. I hope you were able to derive the algorithm. Even if you are not able to derive the algorithm, don't worry. I'll show you my code which I used to submit it, which I used to submit in this problem, and hopefully you'll get the intuition which I am trying to convey. So this is the code. Don't worry, I'll explain line by line. Nums is the array given to us. First one is the base condition. If nums dot length is 1, if we have only single element, obviously that element is the peak of the mountain and it will directly return. Similarly, if length is 2, this is also another base condition, like the maximum of them would be the peak, right? So this I have written here. Okay, so low, this is the classic 3-pointer binary search algorithm in which there is a low pointer, there is a high pointer, and there is a mid. Okay, so this is the while loop. While low is less than equal to high, I'm calculating mid. Now, some subscribers also ask me, like, why you calculate mid like this? You can also do mid is equals to low plus high by 2. So the answer is pretty straightforward actually. Uh, when you'll do low plus high by 2, if both low and high are tending to the integer maximum range, so mid will overflow and some negative value due to cyclicity would come. So to avoid that overflow, you can do something like this. This is better way of calculating the mid actually. And you'll surely get some brownie points if you write mid something like this in the interview. So no problem. This was about the mid. Let's move forward now. So once you calculate the mid, uh, so these two conditions you can leave for now. These two conditions I'll come back then later. You can focus on these if parts. Okay. if nums of mid is greater than nums of mid minus 1 and nums of mid is greater than nums of mid plus 1. Correct. What is this scenario? This is this scenario. Mid is at the mountain peak. Okay. Mid is at the mountain peak and mid minus 1 is here. Correct. Mid minus 1 is here and mid plus 1 is here. Got it. Okay. This is the scenario. So the next line is if mid minus 1 is less than mid and mid is less than mid plus 1, which is this scenario? So nothing but this scenario on the upward slope. This is mid minus 1. This is mid. This is mid plus 1. Okay. This is that scenario. And there is one more scenario possible also, which is in the else part, which is this one, which you can write on your own. So this classic way of converging the subspace, low is equals to mid plus 1. In this case, my subspace, really, in this case, the peak lies on the right side of the mid. So I can ignore this subspace, correct? And similarly, vice versa is true for the downward slope. In the downward slope, clearly peak lies here, and I can just ignore the subspace towards the right. So this way, this algorithm would converge, and finally it will point to the peak. It is also possible that there is no peak in some of the test case, and author has given the test cases like this. So in that case, you can return a -1, and this will come out of the while loop in that case without any valid peak. You can return -1 in that case. I hope like you got the gist of the algorithm. Even if you didn't got this algorithm completely, I highly request you to please go through the video again, and surely you will get the gist of the algorithm and you'll be able to code this on your own. So let's move on to the time and space complexity of this algorithm now. Time complexity is pretty straightforward. If we are dividing the subspace into two halves at each step, so we are converging each time, ignoring half of the subspace. So in that case, the time complexity is O of log of n, and space complexity is O of 1, since we are not using any extra space or extra auxiliary array or extra collection. So this is all I wanted to talk about in this video. So if you liked this video, please like this video, and please subscribe to my channel, Clean Coder, as it gives me a lot of motivation to make these kinds of similar videos. Once again, thanks a lot for watching this video.